Hello, my name is Jenny Kent and I work at the Northwestern University Prosthetics-Orthotics Centre. I'd like to thank AOPA for the opportunity to present this ongoing project today. Today will be a project introduction, as our data collections were unfortunately halted by the COVID-19 lockdown, but the data are on their way. So it's acknowledged that having a well-fitting socket is crucial for a prosthesis user, as it provides the important connection between the prosthesis and the body. This interface, as we know, is not perfect, and some relative movement between socket and residual limb is pretty much inevitable, particularly given the presence of soft tissue. But biomechanically, you could almost think of it as an additional joint, potentially with both rotational movement and longitudinal translation, known as pistoning. The range of motion observed will have a lot to do with the integrity of that interface and the coupling that is achieved between the residual limb and the socket that is maintained during movement. So what's the extent of this? To put some numbers on it, one study within a 2012 review reported over 4 centimetres of translation during walking. So what could this decoupling mean functionally? Relative movement tends to occur when the limb is offloaded, so this could happen on every swing phase of gait. During swing, this would draw the limb downwards, reducing clearance, but it could also potentially compromise awareness and control of the position of the foot, and therefore the placement of the next step. Further, if the socket is decoupled from the residual limb, forces will be transmitted less efficiently. This has implications for the control of the prosthesis and the support it is able to provide, but it also may have sensory consequences. For example, decoupling may delay the perception of foot contact, compromising a person's ability to determine whether the foot has or hasn't contacted the ground, or reduce sensory cues that could give clues about the quality of the ground surface. And this could be highly important for ongoing movement. It's plausible that the uncertainty in the position of the prosthesis, this impaired feedback, and the lack of control of the limb could all be contributing to the high fall incidence in people with amputation. A recent study showed that a high proportion of falls may be due to disruptions to the base of support, which would seem to support this. Vacuum-assisted suspension, in theory, offers a promising solution. With this suspension technique, the socket is sealed using a sleeve. A pump then pulls air out from between the liner and the socket. The below atmospheric pressure created draws the limb in and improves the linkage between the socket and the residual limb, reducing the decoupling problem. Indeed, a number of studies have demonstrated that VAS can reduce pistoning, and isolated studies have reported subjective improvements in proprioception, comfort, and balance confidence. And there's also some evidence suggesting that VAS may be associated with a reduction in absolute fall risk. So the purpose of this study is to explore the effects of improving the coupling between the socket and residual limb using vacuum-assisted suspension on the perception and limb control of transtibial prosthesis users. And we hypothesized that by improving the coupling, we would see improved haptic perception via the prosthesis, so people would be able to feel more through their residual limb, and also an improved ability to utilize and control the prosthesis during standing and walking. We are recruiting 10 adults with a transtibial amputation who are likely K3 level or above, who can walk on a treadmill and can stand and walk for extended periods. Importantly, they need to already use vacuum-assisted suspension, and this is to avoid having to adapt or remake sockets. And this is both for practical purposes, but it also means that we do not have to allow an acclimation period to a new socket or suspension. They need to have a well-fitting, comfortable socket and no skin problems on their residual limb. And finally, no profound peripheral neuropathy, and this is by self-report. We're also recruiting 10 unimpaired control participants of a similar age as a comparison. Our participants are attending 2 sessions at Northwestern University and undergoing 4 tests. There are 2 sensory-related tests in the first session and standing and walking controls tests in the second, and I'll describe these in more detail shortly. We're using a LimLogic active vacuum system to apply the vacuum, and this is attached to the participant's existing socket, then kept in a backpack. All tests are performed in 3 vacuum conditions: baseline, which is a 0 condition, medium at about 8 inches of mercury, and high at about 19 inches of mercury, and order is randomized. We're using a digivac system to enable us to monitor vacuum levels throughout the tests. The first test is vibration perception, and this is to test how easily people can feel things through their prosthesis. And for this, we're using a vibration platform. There are two test conditions. First, partially loaded, which is seated with the heel of the foot resting on the platform, simulating heel strike. And fully loaded, in standing with the other foot on an adjacent platform. The vibration intensity is gradually increased until the participant signals they're able to feel it vibrate, and that level is recorded. We're measuring the vibration using an accelerometer attached to the base of the platform, and our variables of interest are vibration perception thresholds in partially and fully loaded conditions. The next test is based on the general idea that if people are able to sense more through the prosthesis, they may not have to rely on their vision as much for postural control. And for this, we're using a Biodex Balance Master, which has a strain gauge platform to measure postural sway. Participants stand for 30 seconds with their eyes open and then with their eyes closed, and platform data are collected during these periods. The specific variables we're looking at are the difference in sway path length and mean velocity of sway between the two conditions, and these are frequently reported measures of postural stability. The difference between the two visual conditions provides a measure of their person's reliance on vision. In order to test standing control, we're using the limits of stability test of the Biodex system. In this, participants stand on the instrumented platform, then are asked to lean their body to move a cursor towards 8 targets, with order randomized. For each vacuum setting, we are computing the time to complete the task and the deviation from the direct path to each of the targets. Finally, in order to test participants' control during walking, we're using an instrumented treadmill with augmented reality. The system allows us to project visual targets that move synchronously with a belt. For this study, we're using a stepping stone task, and participants are asked to step on rectangles projected onto the belt. They complete a 2.5-minute sequence with targeting and undisturbed walking periods. The centre of pressure is measured during single limb stance when only one foot is on the belt, and then used to compute 2 variables. The first is step width variability during the phases without stepping stones, and this is a measure of walking stability that has been related to falls and fall risk. The second is mean targeting error during the stepping stones trials as a measure of limb control during walking. So this is what we expect. We anticipate that higher vacuum levels will be associated with improved haptic perception, so we will see lower vibration perception thresholds, suggesting that participants are able to sense more through their prosthesis, alongside smaller differences in sway metrics, indicating less reliance on vision in standing. Also, improved control, so we will see a higher intentional sway accuracy, indicating participants have better control of their body above their prosthesis, alongside reduced step width variability and targeting error, indicating that they have a better control of their prosthetic limb. Should our hypotheses be supported, we hope this work will provide further clinical evidence regarding the importance of interface integrity, and this is of a direct relevance to the prescription and configuration of vacuum-assisted suspension systems. And with that, I'd like to thank my co-authors and the study team, the VA for use of the motion laboratory, and AOPA for funding this work. And I'd welcome any questions. Thank you.